Hey everybody, I'm Shashank at Modular, and in this video we'll take a look at how you can port your Python code to Mojo for huge performance benefits. We'll use a specific example of k-means clustering. We'll implement this in Python and in Mojo and show you the key code changes that you need to do to go from Python to Mojo. We'll also run it and compare the results with standard implementations like scikit-learn to make sure they're all doing the right thing. Now this video accompanies this blog post that we did earlier called Fast K-Means Clustering in Mojo, Guide to Porting Python to Mojo. Now this blog post has step-by-step instructions on what we're going to cover. It also has links to the code that we use in order to implement the Python and Mojo implementations of K-means. In this video, I'll walk through step-by-step some of these implementation details and what code changes you need to make. Before we jump into the implementation, first let's do a quick recap of what k-means clustering really is. Now if you're a machine learning expert, you already know what this is, but if you're not, bear with me for a few minutes while we set up this problem. Let's say you drive a stick shift car, and right in front of you as a driver you see the speedometer and the tachometer. The speedometer shows you the vehicle speed in miles per hour, and the tachometer shows the RPM or revolutions per minute. Now, if you take the data of these sensors here and put them into a table, you get this nice little table where each row is the sample that you gather and each column is the two features that we have. So this is two-dimensional in columns, which is miles per hour and RPM. Now, if you take this data and plot it, you'll see something like this on the right here. Now to the naked eye, you'll see that there are some patterns in this data. They're not fully random. You'll see that there are clusters here that look like this long finger-like things. And you look at this and you know there is some sort of a structure within the data when you plot this. Now, if you're a trained mechanic, or you know a lot about cars and gear ratios, you'll know that this data set actually represents the values of vehicle speed and engine based on the gear ratio. Now, how do I get these kind of natural groupings or structures, or how do I find them? That's where algorithms like k-means clustering come into play. So you take this data set, plug it into an algorithm called k-means, specify the number of clusters. If you don't know the number of clusters, there are other techniques that you can use to find the optimal number of clusters. Let's say you know there are 5 clusters, and what the algorithm spits out is cluster centroids, these dots here, blue dots, and the data set or each of these samples representing each of these black dots and which cluster they belong to. So k-means clustering will give you that. Now consider that your data set is not two-dimensional but tens of thousands or hundreds of thousands of columns. Now you can't really visualize that, so you can't really plot and see if there's any structure, but an algorithm like k-means can automatically find these groups for you by grouping data together. A good example could be an e-commerce data set where each row is a customer and each column is customer demographic information, and k-means can run clustering and find that specific customer groups have similar preferences that you may use to maybe sell new products and such. So how does k-means clustering really work? So when you call the fit function here this way, it executes an algorithm that's pretty straightforward and looks like this. First, it'll find random centroids within your data set, and we use a method called kmeans++ that means that the initial centroid is not fully random. They are may ensure that they're not grouped together, so they're not all lumped together next to each other, but you get some initial centroids that are not the right centroids. Then you go through this iterative process here. So this iterative process here, this loop, will go through the process of updating the centroids with each iteration called the Lloyd's iteration in order to find the right set of centroids, and when the algorithms converged based on some convergence criteria, you have the optimal number of clusters we see here. Okay, with that primer out of the way, let's go take a look at the code and what the Python and the Mojo implementation look like. So in the blog post, there is a skeleton structure for both the Python and the Mojo class. I'll show this to you and jump into VS Code to show the actual implementation. But this is a nice to show you a high level structure of the Python class and the Mojo struct and the key sort of differences. So the Python class has the init function. The Mojo struct also has an init function. Then there are key functions that we need, which is to calculate the distance between points and centroids using distance norm, kmeans plus initialization to get those initial centroids, Lloyd's iteration that we run in a loop in order to get the update the centroids, and finally the fit function that orchestrates all of this. And the key difference between the Python and the Mojo implementation is showed in these red boxes. So the first thing that jumps out is we've added types to all the variables, all the arguments. Now, if you're used to writing typed Python code, this looks familiar to you. So you can add types, and Mojo being a compiled language, the types are actually helpful for the compiler to optimize and give you better performance, which is why we see better performance with Mojo. In addition to that, we also add return types, but there are a few other changes that you'll see in the implementation itself. Now, why do we want to port this to Mojo? We will go through the performance benefits at the end of the video, but you can see up to 6x to 250x or more when you port from Python to Mojo, and Mojo also scales better as you increase the number of data set sizes, the number of clusters, or number of features. Okay, so let's head over to Visual Studio, and here we have the Mojo package that implements kmeans, and also the Python package that implements kmeans, and we have some helper functions to benchmark the implementations and to run both those implementations. Okay, so let's open up the run kmeans and show you the key differences between the APIs. We've tried to keep the APIs same. The added benefit of Mojo is that Mojo has great Python interoperability. What this means is that you can actually import Python functions, Python modules, and run them within Mojo, and it's going to call CPython in order to execute them. So you can stay in one language and execute Mojo code and Python code. So let's go to the section where we compare the APIs. So the Mojo API looks like this, and you'll see that first we create a Mojo model using kmeans and specify the number of clusters, and then you call the fit function. Okay, and the Python implementation is also very similar. You call the Python kmeans function and call the Python fit function. Now these have been modeled after a standard implementation, which is the scikit-learn implementation, which you can also call through Mojo because Mojo can call Python function. So there's the scikit-learn kmeans where you specify the clusters and also the fit function. Okay, let's go ahead and run this and take a look at the results. Okay, so on executing this, you'll see that there are a bunch of clusters, and the star represents the Python implementation centroids, the triangle, the Mojo implementation centroids, and the red dot is the actual centroid. So for a lot of these clusters, all these three implementations give similar results. Some of them are a little out here, which means that they didn't give you a better result as some of the other implementation. So you'll see here that the inertia is a value that shows convergence of this algorithm, and the Mojo implementation, scikit implementation have almost pretty much the exact value till several digits after the decimal. The Python implementation didn't give us higher the number means it didn't converge to didn't give us a better result, and this is not the fault of the Python implementation. This is sort of a stochastic process wherein it's very sensitive to initial run. If you actually run this again, you'll see that you'll get slightly different results for each of these implementation. So now you'll see that the results are much closer between Mojo and Python, and scikit-learn gives you slightly different results. and also the number of steps it takes to converge. The interesting thing is you'll also see some speed up information here for this configuration. Okay, so that's how you run them. Now let's take a look at the code side by side and compare them. So this is the Python implementation and the Mojo implementation, and we'll do compare selected and take a look at some of the key code changes. So as I showed you before, in Python you have a class kmeans, in Mojo I have a struct, and the key difference in the init function here is that they're mostly same. So anything that's not highlighted is no changes, no code changes. Where there are code changes, we've added types. So the number of clusters has a type of int, max iteration has a type of int, scalar int, boolean. Okay, if you remove the types, the code is very similar. There's almost no code changes. The other interesting change here is centroids is an empty list that we initialize. Python being dynamic language, you can update the list dynamically as you add more centroids to that list, whereas in Mojo, being the struct being compile time bound, we specified the list, but we also specified its capacity so that the memory is allocated. This gives you better performance as well. Other than that, the init functions looks very similar. Now let's go all the way down to the fit function that orchestrates the whole fitting process for k-means clustering. So on the left again is the Python implementation and the right is the Mojo implementation. So in the Python implementation, you see everything that's not highlighted with red or green are the same code. Okay, running through this quickly, first we initialize a matrix called centroid distance, which has the same number of samples as our data set and number of columns equal to the number of centroids. And the value for every sample and every centroid is the Euclidean distance, squared Euclidean distance between that sample and that centroid. This is the most computationally intensive part of this algorithm, finding the distance from every sample in the data set to every centroid. And that is where Mojo gives you better performance, and we'll see how. We initialize it using NumPy. Now Python has NumPy to use as a matrix data structure, whereas Mojo doesn't have a NumPy equivalent. So I've shared a matrix implementation, and you'll see this within the Mojo implementation here. It's called matrix.mojo. I've implemented it just for this example, and you can use it to hold two-dimensional matrices. So all of these types are of matrix types. Whenever you have a NumPy array, you have a matrix type here. We then call kmeans++, which is the same code in both, that initializes the initial centroids, and later we call the Lloyd's iteration, which iterates in a loop. So you see we loop from 1 to range of self dot max iterations. So we have a max number of iterations, we can iterate till then, unless we reach a convergence criteria where the inertia value doesn't change. We'll talk about what inertia is. If it doesn't change, then we exit sooner. And Lloyd's iteration is the one that updates the centroid. So anything that's not highlighted is the same code. The key difference is again here, instead of using NumPy, we use the Mojo standard library math functions. Okay, so fit function calls kmeans++ and Lloyd's iteration. So let's take a look at kmeans++. Now again, the kmeans++, anything that's not highlighted is the same code, no changes between Python and Mojo. But the few places where they're different is of course where we've added types. We also have keyword called inout here, which is new to you if you're a Python user. It basically means that a variable with keyword inout is a mutable argument, which means any changes you make in the function is visible outside the function. In Python, this behavior is not explicitly defined. For example, NumPy arrays can be changed in a function. The values are reflected outside unless you make a copy or you write to it or you assign it, then copy is made. So the behavior is not explicitly defined, whereas in Mojo you can explicitly define it to be inout, owned, or borrowed, depending on if you want to make a mutable reference or immutable reference or make a copy and all of that. So Mojo gives you control over the ownership and memory management. Other than that, we initialize these matrices. We initialize a random centroid to start with. Instead of using NumPy functions, we use the standard library functions. Rest of the code is very similar. In a loop, we calculate the centroid distances, find the minimum distance to assign a data point to that specific centroid. So if the distance between a data point and one of the centroids is closer, then we say that data point belongs to that cluster defined by that centroid. Okay. We go through this, and in the kmeans++ will give you the initial set of centroids. The magic happens in Lloyd's iteration. Again, anything that's not highlighted is no code changes. So in Lloyd's iteration, the key difference is that key magic here is that we calculate the distance norm from every data point to every centroid, and this happens in the distance norm function, which we'll take a look at the last, which is where Mojo gives you where you can unleash the Mojo superpowers. But once you have the distance matrix, you can calculate the labels, as I mentioned, depending on which cluster is closest to each data point. And we use very Pythonic way to assign, to calculate the centroids. And the code is very similar in Mojo and Python. I won't go through every line here. And finally, we calculate the inertia value, which we use as a convergence criteria to stop the algorithm. Okay, so finally, we'll take a look at the distance norm calculation. So this function is wildly different because in Python, we take advantage of NumPy's linear algebra package to run optimized Euclidean distance calculation. Bear in mind that linear package and the NumPy package is written in C, low-level C, hundreds of lines of code of optimized C code that runs very fast on hardware, takes advantage of hardware resources. So this simple function is actually hiding hundreds of lines of code. But what we do instead in Mojo is re-implement that line of code in pure Mojo. And again, without getting into all the nitty-gritty details of this function, it's discussed in the blog post. Broadly, there's a function which we parallelize the calculation of distances from each data point to specific centroid. If you have 5 centroids, then the distance calculation from all the data points to each centroid happens in parallel. Okay. Within each parallel calculation, we also vectorize the Euclidean distance calculation. So if you consider an array for each data point is an array and the centroid is another array, the Euclid distance is the difference between these two arrays with squaring of each terms and adding them all up. And you can do this in a vectorized way by processing not individual elements in a row, but SIMD width elements. SIMD width depends on your processor. Different processors have different SIMD width, but if your SIMD width is 4, then you can process 4 elements at the same time, and that's exactly what we do here. So in this loop, in the first loop here, we process we calculate the Euclidean distance running through SIMD width elements at a time. So you're doing it in a vectorized way, and because SIMD width happens to be or should be a power of 2, if your number of elements exceeds that, then there are a few spillover elements, and we process that separately individually, and then we calculate the centroid distances this way. Now if you're not a systems programmer, if you're a pure Python programmer, this may look a little intimidating, but these are the few places where you can unleash the power of Mojo and actually program at a very low level to get the performance that you need without relying on or without having to go write C++ code and take advantage of platform specific libraries and all that. You can write it in pure Mojo and get much better performance. Okay, so that is a quick comparison of the two functions. And again, the blog post, as I mentioned, goes through step by step what happens in each code. For example, when we take a look at Lloyd's iteration, so we compare the key differences here and what happens in each line, and also what changes we did. So I highly encourage you to also check out the blog post. With that, the last thing I want to show you is that we also have a benchmark function here that benchmarks both the implementations. I'm not going to run this, but because we do this huge sweep across various sample sizes and number of clusters and number of features, what I'll do instead is show you the final results of the benchmark sweep. So in the blog post, if you scroll down, you'll see here that in the first plot, we freeze the number of samples and features, and we vary the number of clusters. So as you increase the number of clusters, you see that Mojo scales very well, whereas Python time to calculation keeps increasing up to the point that it becomes 250 times faster. If I run this for more number of clusters, it would keep diverging and you get better performance with Mojo. And in the second graph, we keep the sample size and the clusters fixed, and we vary the number of features, which is the number of columns. And here you see that the gap is pretty stagnant. We still see anything between 13 to 16x speed up. And in the last graph, we see that when we hold the number of clusters and features constant, whereas vary the sample size, it's a little more balanced, the speed up. The median speed up of 150 times faster with Mojo, but both of them scale very well. So you can get good performance benefits based on whichever variables you're using, which is this is an example of why it's hard to say exactly how much faster Mojo is, because it's really dependent on your problem, really dependent on your specific configurations, how optimized your code is, and so on and so forth. With that, I'll conclude this video by saying, please check out this blog post for a more deeper analysis, and also the code for this blog post is available on GitHub, which is also linked from the blog post. We'll also add a link to it in the YouTube video right below. So try it out, run it, let us know if you have any questions, and please join Discord, where we have interesting conversations about Mojo, and share your implementations or ask your questions there. With that, I would like to thank you for watching this video, and stay tuned for more videos. Bye.